I definitely think we'll benefit from thinking of the 2.00x as 2 plus some tiny little fraction, it would be x over 1,000, and the 3.00y as 3 plus some tiny little fraction, in this case y over 1,000. Because then when we multiply the first term by 3, we get 6 plus 3x over 1,000, and when we multiply the second term by 2, we get also 6, but this time plus 2y over 1,000. Now, since the 6 and the 6 are a match, what this question is really asking is 3x greater than 2y? And that actually makes statement 1 fairly easy to evaluate. Statement 1 tells us the exact opposite. It says, no, 3x is less than 2y. It's not greater than 2y. So we definitely start with statement 1, and we can go ahead and eliminate the answer choices that claim that statement 1 is not sufficient on its own, because it gives us a definitive answer. It gives us a definitive no, and that is sufficient. So we can eliminate B, C, and E. Now, statement 2, I think, is a lot more challenging, and we should go ahead and evaluate that right after this. So what's so tricky about statement 2? We wanted to know, is 3x greater than 2y? And statement 2 just tells us that x is to the left of y minus 3 on the number line. Now, if we didn't know anything else about x and y, this statement doesn't have a chance of being sufficient. Why would knowing the relative order of x and y minus 3 on the number line, why would that be enough for us to infer whether or not 3x is greater than 2y? There are so many different ways that that could play out on the number line. However, we do know something else that's really important about x and y. We know that they are digits. What could digits be? There's only 10. There's only 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And we know that x belongs to that set, and we know that y belongs to that set. So that really limits the number of possible values for x and for y. So in that context, when we're told that x is to the left of y minus 3 on the number line, knowing that at most y is 9, that means that at most x is 5. The question wanted to know, is 3x greater than 2y? So even if you maximize x all the way up to 5, is 3x greater than 2y, where x is 5 and y is 9? Is 15 greater than 18? No. And that's when we really maximize x. Do we also need to check smaller values of x and y? I mean, if I make y, let's say, the smallest y could be is 4, in the event that x is 0, is 3 times 0 greater than... No, it won't be greater than anything positive. What about 3 times 1 versus... the smallest value y could be is 5 in that case. Is 3 times 1 greater than 2 times 5? No, of course not. The reason that I'm looking to minimize y for a given x, or alternatively to maximize x for a given y, is because we're trying to see whether or not it's possible for 3x to be greater than 2y. So if I want, if I'm trying my best to enable 3x to be greater than 2y, given that they're both positive, I'd want to maximize my x and minimize my y. And we can see that given the constraint that they are digits, and given that x is smaller than y minus 3, it's impossible to ever get a scenario where 3x is greater than 2y. And therefore, this statement is also sufficient on its own, and the correct answer is D. If you found this video useful, go to quantreasoning.com for a lot more where that came from. You should also click that like button and let me know in the comments below what you'd like me to make future videos about. And of course, if you haven't yet subscribed, go ahead and do that and click that bell below so you get notified about future videos. See you next time.